Welcome to The Explainer. Today, we're jumping right into demystifying the massive, high-pressure equipment that actually makes offshore energy production possible. We are talking about process pressure vessels.
Okay, let's dive into this. If piping is the circulatory system of an offshore platform, pressure vessels are the organs. It's such a powerful metaphor because it really grounds this highly technical engineering in a biological concept we all instantly get. The pipes, well, they simply move the fluid around. But the pressure vessels, that is where the actual work happens. It's where the crude oil, the gas, and the water are separated out, where the gas is dried, and where the produced water is cleaned. So understanding exactly what each vessel does and how it pulls off its specific function is literally the absolute foundation of understanding offshore production.
So let's start with the absolute workhorse of any production platform, the production separator. If we're sticking with our biological metaphor, think of this as the stomach of the platform. This is the very first place the well stream arrives after leaving the manifolds. And you have to imagine, this well stream is a completely chaotic, turbulent mixture of crude oil, gas, and water coming in under immense pressure. As it enters the separator, it immediately slams into an inlet diverter. This is a simple but absolutely crucial baffle that deflects the incoming flow. It essentially acts as a giant shock absorber, violently reducing the fluid's energy, which causes the heavier liquids to immediately fall and the gas to start rising. What follows that initial violent impact is actually a beautifully controlled three-phase gravity separation. It's all about density. The gas naturally vents right to the top outlet, while the liquid phases settle down below. Because oil is less dense than water, it forms a distinct layer floating right on top of it. This natural stratification allows us to isolate and extract all three specific phases simultaneously, using controlled level outlets. And that's exactly why we call it a three-phase separator, because it successfully isolates gas, oil, and water into pure streams under perfectly controlled conditions.
Now, what's really interesting about this slide is how these internal components basically act as the separator's digestive tract to prevent cross-contamination. You've got straightening vanes in there that calm the liquid down, reducing turbulence so the separation can happen as smoothly as possible. Up at the gas outlet, there's a mist eliminator, which is usually this thick mesh pad, and its job is to catch any rogue liquid droplets trying to escape with the gas. Down in the liquid section, there is a physical wall called a weir that maintains the oil layer perfectly above the water interface. And right at the bottom outlets, you have a vortex breaker. This literally stops spinning whirlpools from forming, which completely prevents gas from getting sucked down into your liquid lines.
So all of that sounds very smooth and highly controlled, right? But what happens when the pipeline suddenly decides to fire a literal cannon blast of liquid at the platform? You see, in offshore engineering, especially when you're dealing with long subsea pipelines, there is this incredibly dangerous phenomenon known as slugging. Basically, liquids like condensate and water can pool up in the low points of a pipeline on the seafloor. The gas pressure builds and builds behind those pools until, suddenly, it launches a massive surge of liquid toward the platform. Imagine a fire hose that, instead of spraying a steady stream, just intermittently fires a devastating cannon blast of water. If a surge like that hits our standard production separator, it would completely flood it and overflow right into the sensitive gas systems.
To handle that kind of violent physical challenge, engineers use a highly specialized vessel called a slug catcher. This is a large-bore buffer vessel designed for one exclusive purpose: to absorb those sudden, massive surges of liquid. Now, the most common type you'll see is the finger slug catcher. So instead of one giant, unwieldy tank, it's actually a series of massive pipes arranged in parallel. This provides an enormous holding volume. It basically catches the slug, buffers that chaotic arrival of the liquid, and then feeds it smoothly into the normal processing system at a steady, manageable rate. It completely prevents catastrophic flooding downstream. All right, if the separator is the stomach, these next vessels are definitely the kidneys. Here, we're looking at two entirely different physical solutions for separation. You have the gravity-based gas scrubber on the left and the centrifugal hydrocyclone on the right. Both of these are tasked with purifying a very specific stream, but they go about it in completely different ways depending on what phase of fluid they're actually handling.
The absolutely crucial point to understand here is the incredibly high stakes of gas separation. That is exactly where the scrubber comes in. You have to remember, compressors are designed to compress gas, and gas only. Liquids are essentially incompressible, so if even a tiny amount of liquid carries over into a gas compressor, it acts almost like a solid object slamming into those rapidly spinning metal blades. The result is instant, catastrophic mechanical damage. So scrubbers sit right upstream of the compressors. By using demister pads and gravity, they ensure that every single liquid droplet is stripped out before the gas ever touches that delicate, highly expensive machinery.
Now, over on the liquid side, we have the hydrocyclone, and this deals exclusively with separating oil from water. But instead of relying on gravity, it uses centrifugal force. The contaminated water gets injected tangentially into this cone-shaped vessel, and that creates a fierce, spinning vortex. Because the water is denser, the centrifugal force flings it right to the outer wall where it exits downward. Meanwhile, the lighter oil forms a tight core in the center and spirals upward to exit out the top. It is just elegant physics. And the best part? It has 0 moving parts, which allows it to process incredibly massive volumes of liquid efficiently without breaking down.
But here's the reality. Gravity alone isn't always fast enough. Sometimes, the oil droplets trapped in the water are microscopic. According to Stokes' law, a tiny droplet takes a very, very long time to naturally rise to the surface. But Stokes' law also tells us something incredibly useful. If you double a droplet's diameter, you quadruple its rise velocity. And this brilliantly illustrates exactly why engineers use a coalescer. It uses a dense packing material, like corrugated metal plates or a structured polymer matrix, to force the fluid through very tight spaces. Hundreds of these microscopic droplets crash into each other on these surfaces and merge into much larger drops. By artificially increasing the droplet size, the coalescer exponentially speeds up the gravity separation process.
So why do we need hydrocyclones and coalescers and all of this intense multi-stage polishing in the first place? Well, it all comes down to this exact number: 30 milligrams per liter. That's 30 parts per million. This is the incredibly small, strictly enforced margin of error allowed by regulators for operations in places like the North Sea. Before any produced water can be discharged overboard into the ocean, it absolutely must contain less than 30 parts per million of oil. They have continuous oil and water analyzers monitoring this 24/7. It's a real testament to the fact that these pressure vessels aren't just heavy industrial plumbing, they are ultra-precise environmental protection tools.
Because here is the challenge. As these oil reservoirs age, they start producing more and more water, sometimes reaching ratios of 95% water to just 5% oil. We are asking these giant steel organs to process thousands of tons of violent, high-pressure fluids every single day, all while maintaining those microscopic environmental tolerances. As we push further into deeper waters, how will these tightening demands continue to shape the future of offshore engineering? It's a massive challenge. Thanks for joining us for this explainer.